G'day. Today's video is in two parts. The first part's looking at true theoretical and experimental probability, trying to build on our understanding from previous years and the previous lesson in this online series. And then we're going on to one of the first new bits of probability theory, looking at the multiplication principle. So the first thing is looking at true probability. Is that true probability in most situations is always unknown. It's the actual probability that the event occurs. So we can't predict the future, but it's and there's always slight differences from what the theory tells us. So the example they've given there is that looking at flipping a coin, and we know that if the coin's fair, it should be 50-50. However, if you actually got a coin and carried out this experiment, you wouldn't get 50-50, or one side is slightly heavier on the other side. So while the probability wouldn't be noticed if you flipped it 1,000 times so much, over a long period of time, you'd be able to see that there's a slightly greater chance of getting tails because the head side has more metal and it weighs more. Experimental probability is the probability obtained from the experiment. So if we took a coin, we flipped it 50 times, we get 22 heads, then the probability of getting a head, or the experimental probability of getting a head, is 0.44. So that's obviously slightly different from the 0.5 we would expect from theoretical probability. This is fine. It's just one of those things. It's unlikely, but there is still a chance that if you flip a coin 50 times that you'll get heads 50 times. It doesn't mean that the probability of getting heads is 100%. What we do find with experimental probability is that the more you do it, the closer it is to the the theoretical probability. So it would be unlikely if you did it 1,000 times, the probability of getting 1,000 heads is very, very small and unlikely. The other thing is it talks about this long frequency, and we tend to use this for events that we don't know what the theoretical probability is. Things with many variables, like the example I used before with the probability of a yellow car coming down a particular road. There's no way of knowing all the outcomes and things like that. So we can sometimes use simulations or long-run experiments to be able to work out this answer. So I've got a simulation here that looks at coin flipping. So this is our experiment. This is a spreadsheet that's been set up for a number of coin flips, and then you can see if I press this button, it changes the number of coin flips. You can see the first flip was heads, and so far we've ended up with one head so far, so we have a probability of 100%. Now, if we stop there and said that our experimental probability is this, so that's our estimate of theoretical probability, we know that we are wrong. But as you can see, as we go through, we do two flips and we've got a tails, so suddenly it drops down to our 50%. So suddenly after two, we would be correct with our theoretical probability. If we increase this, you can see as it goes along, we end up with a slightly different value here. Now, these graphs on the side are showing how the probability changes over time. So we started off at 100, and we went to 50, and then it goes off. So as you can see, as I'm increasing those probabilities, that the numbers are still changing. So as I get up to 20 flips, we're ending up with it slightly varied. So that's our first 10. You can see it started off at 100, but then it bounced off to 50% exactly. but there's still some variation with each one. So now this graph carries on for the next 100. I carry on. So what we can see with 100 flips is that we are ending up with, it's still changing, so we're pretty close to 0.6. However, you'll notice that the changes are getting smaller and smaller and smaller, and we're starting to flatten off. From 100, this graph will take over, and it will start to look at if we do 100 flips. 500 flips, sorry. So if we stop at 499 flips there, what we can see is that we end up with a graph that has little variation now, and it's balanced out at our 50%. If we can scroll down, or our 0.5, you can see that the probability is getting very, very small. Sorry, the changes are getting very, very small, and you can see it's now balancing out at 50%. So while this is a familiar example, you can see that as we carry out an experiment or a long run experiment, the more trials that we complete, we end up with a much more balanced answer. And that answer is closer to the theoretical probability. So the theoretical probability that we would expect comes from models. So there's a number of models that, and we study these in more depth in the other external we're doing this year on probability distributions, particularly looking at Poisson, normal distribution, rectangular distribution, and triangular distribution. And there's some things to remember, that these are only models, they're not perfect. They tend to use straight lines and blocks and things like that, where in reality those models don't fit. So originally I said that this video was in 2 parts. The first part was discussing theoretical, true, and experimental probability. Second part is looking at something called arranging and choosing. So the important thing that we need to know when we're looking at probabilities is, first of all, the number of favourable outcomes, but also the total number of outcomes. So arranging and choosing is one way that we can work out those values without actually having to physically count them ourselves. So it's a pretty simple concept, but if we think about looking at Prather's is shopping for a car, the dealer tells her that she has 3 different models, and also that each model comes in 5 different colors. So what we want to know is, if we're going to work out the probability of the type of car she chooses, we need to know how many possible combinations are there. So a use of a tree diagram is quite a good way to do that, because we know that there is 3 options for Prather of the model, either A, B, or C. And we can put branches to those. But we also know off each branch there are 5 options of white, red, blue, yellow, green. So with these 5 options, and then obviously there is for B and C. So you need to put the whole graph together to work those out. And you can see here is the graph finished off that A, B, and C have 5 options. So we have obviously model A that's white, model A that's red, and so on. And if we count out that, we end up with 15 different options. Now, looking at that, I tell you, a tree diagram is a really good way to work that out. However, it is quite time consuming. Is there a way that we could have actually worked out that answer without the tree diagram? It's actually looking at the number of options. So we've got 3 different models, and we've got 5 different colors. So actually what you can do is just take each model and color and times them together. So 3 times 5. And this works for a number of situations as long as you know how many outcomes there are. So this is the fundamental counting principle, also called the multiplication principle. That is simply a task of finding each stage, how many options there are or choices there are, and multiplying them together. So a toy manufacturer makes a wooden toy in 3 parts. The top part will be red, white, and blue. So 3 options. The middle part will be orange or black. So there are 2 options. So the third one, the bottom part, will be yellow, green, pink, or purple, which is 4 options. That leaves us with working out the number of different options there are for the top, the middle, and the bottom would be 2 times 3 times 4, which would give us 24. So in a tree diagram, you can create that and count them up, but that's a lot of work compared to just being able to go 3 times 2 times 4, which means 24 in total. So that's not the only thing we have to worry about. What about if instead we're doing at different stages? What about if we're using the same options and we want to be able to place them to work out how many different options there are? So the example is if I have to have arrange 5 different items in a row, how many ways can I do this? So the first thing is to do is label those 5 items A, B, C, and D. Now, for the first of one of the 5, so the first thing we're going to line up, there can be, it's one of the 5. So either A can be first, B can be second, A can be first, B could be first, C could be first, D could be first, E could be first. Now, once I then take my second option, then we have to think about what could go in the second place. Now, if I use A to start with, suddenly that's no longer an option anymore. So we can't use the same idea that we had before, where we could go 5 times 5 times 5 for all the places. So if A is being used as the first letter, then I can only use B, C, D, and E. Next, if B is the first letter, then I can only use A, C, D, and E, and so on. And that's the same for all the different letters. So if we think about how we're calculating this, that for the first place, we have 5 as our option. But for the second letter, we have 4 to choose from 4. So what you end up with is, of these letters, we have 20. Now, carrying out the rest of the places, that obviously we have, if A and B are the first 2 letters, then we only have 3 to place in the third place. And then that can be repeated over and over again. So this gives us the arrangement of 5 times 4 times 3. Now, obviously for the 4th letter, you've only got 2 letters left. And then obviously for the 5th letter, you have to use that letter and it's not going to go anywhere. So what you work out is to calculate it is it's 5 times 4 times 3 times 2 times 1, which is 20 times 3 is 60, 120.